First up, we're going to have a quick lightning talk, and then we're going to have a panel. So let me get off the stage here and introduce kind of Jason to talk about quantum.
Oh, thank you. Is this on, Jess? Okay. Yeah, so I want to talk about making quantum computing mission capable for software verification and validation, or software VV as I'll refer to it. So you had a bunch of talks before this one talking about a lot of the difficulties with software VV. I'm Jason. I'm a research scientist at SAM-USCI, in particular in the Emerging Technology Center. I'm missing some text, but the purpose here is that we're taking a software VV, which is a core SCI mission, and we want to apply emerging advanced computing technology to that research. Okay, so why is software VV important and hard for the DoD? Well, we've already seen examples previous, but basically, on average, across all of these complex software engineering systems in the DoD space, like VV is like half the cost of delivering software, and in some cases, like the majority of the cost. And so accomplishing the task of doing formal verification and validation in computers is hard because the computational cost of the methods used is very costly. That is, typically speaking, for the more advanced methods, this cost scales is exponentially with the system size. So as a pretty picture demonstration, not sure what happened there. Ah, here we go. Yeah. There we go. Okay. So this is a video of a software project for a UAV, and this is actually just one small component of the entire UAV autopilot system. This is showing the software, the code base exploding in size and over the course of days and months, and we've got hundreds of developers all interacting with the code. So this is really the problem that we're facing, is that not only do these methods really scale badly with size, that actually the size of our projects are also getting bigger. So this is like going from the F-22 to combat UAV and the projected number of lines of code that it'll require. All this really is saying, like, we need to look at new computing paradigms to try and tackle these problems. So one candidate for a new paradigm is quantum computing. So we have here, back the last century or so, the 5 major computing paradigms from electromechanical to integrated circuit. And what people are looking for is this next generation, this next paradigm. And people think that quantum computing could be it. These aren't showing up, but basically over here, not just in industry, but also in government and the DoD in particular, they've recognized this, the hype that you're hearing about quantum computing recently and are investing. So the question then is, basically, what is the path towards mission capability for quantum computing? This is a really hard problem. There's a lot of unanswered questions. This field is in a nascent state. So over here, basically, the question is, how do we take these hard problems and express them as quantum algorithms or quantum circuits? This is what this diagram is. These quantum circuits basically dictate the interactions and behavior of qubits, which are the fundamental computing elements of quantum computers, the analog of classical bits. But there is so much that's not understood about this process, the limitations, and then finally, how do we take these programs and execute them on quantum computers and actually measure a wall time speedup over classical computers? So all of this has not been demonstrated, and actually there's a prize within the community looking for a $1 million prize for showing this kind of speed up. And as I said, there's many challenges here, but the potential computing power is what is driving this forward, and it could enable the next generation of software VV tools. And if you want to talk to me any more about that after, which I didn't start the timer, so I don't know how much time I have left, I'll be available. So thank you. Is that 5 minutes? Anyone have any idea? Close enough. It is now.